chapter, which is chemical kinetics. This is definitely one of the more challenging chapters in this course. There's actually quite a few challenging ones, so please, again, make sure you're reading your chapters, doing your homework, and asking questions when you need. Okay, so let's go ahead and get started. So basically, whoops, we're not going to get started yet, are we? Okay, so chemical kinetics is just the study of the rate of progress of a chemical reaction. So basically, how fast does a chemical reaction occur? Some occur instantaneous, basically, femtoseconds. Others can take literally millions of years, right? So burning hydrogen and oxygen occurs like that. It's very explosive, it's very quick. Converting coal, graphite, into diamond literally takes millions of years. So there's your two extremes. You have very, very fast reactions, and some are very, very slow, and you got anything in between as well, okay? And we're going to find out that it depends on the concentrations of reactants and products, including if the gas is involved. It could depend on pressures. If it's endothermic or exothermic, it'll depend on temperature. So in fact, it always, regardless if it's endothermic or exothermic, a chemical reaction always speeds up with an increase in temperature. And you'll understand once we start talking about the whys, the physical reasons why chemical reactions occur and what has to happen for that chemical reaction to occur. You understand that it's always going to increase with temperature. So again, concentrations of reactants and products. Now we're going to focus on just the reactants, but we will talk about how the products can also be involved. Again, molarity for solutions, if you have aqueous solutions, pressures, if gases are involved. Concentration of a catalyst. So we'll talk about what a catalyst is. A catalyst is something you add to a chemical reaction that makes it speed up, but it itself isn't consumed in the chemical reaction, so it remains unchanged from beginning to end, but it did influence the kinetics. It made the reaction speed up. We're going to talk about how temperature, always an increase in temperature, will always result in a faster chemical reaction. And then the surface area of a solid reactant or catalyst, okay? Okay, so, and what do I mean by that? Well, if the catalyst, again, if it's a solid catalyst, okay, or solid reactant, depending on what it is, but it's easier to think about a solid catalyst. Well, the chemical reaction can only occur at the surface, right? It can't penetrate the solid. So if you take a big piece of rock and it's your catalyst, well, the catalytic reaction can only occur on the surface of the rock. The chemistry can only occur on the surface of the rock. But if you break that rock in half, well, you still have all the surface area of the outer rock, but now you have those, where the rock was broken, you now have surface area on both sides of that break. So you've increased the surface area. And again, you just keep breaking the rock into smaller and smaller and smaller and smaller pieces, and you just keep increasing the surface area more and more and more, which is just going to make the chemical reaction go faster and faster and faster, okay? Now, chemical reactions proceed, like I said, over a very wide time scale, from literally femtoseconds, 10 to the negative 15 seconds, 10 to the negative 15 seconds, the whole way up to literally millennia. So thousands, millions of years, okay? Chemical kinetics is basically the study of reaction rates and the effects of varying conditions under which the reaction is run. So in other words, we're going to play around with concentrations, temperatures, pressures, and we're going to see how that affects the chemical reaction. That information is actually going to allow us to understand what's going on at the molecular level. We'll actually be able to start to understand why this molecule reacted with this other molecule, but it doesn't react with this other molecule over here, okay? Now, collision theory, so that's how we're going to look at the physical nature of these chemical reactions. So collision theory, we're talking about the actual molecular scale. one molecule reacting with another molecule. It assumes that our reactants, it assumes that for a reaction to occur, that they must collide with sufficient energy. So they have to have enough energy when they collide. And on top of that, they have to be properly oriented. So they have to hit each other with the proper orientation. Okay. The minimum energy of collision that's going to be required for a reaction to occur is called the activation energy. And the variable for activation energy is EA. And the energy, the units for activation energy are going to be kilojoules per mole. Okay. So there's the variable, E subscript lowercase a, and the variables are going to be in kilojoules per mole. Okay, so a reaction, again, is only going to occur if it has the proper orientation. We're assuming that it has enough energy. The energy provided is greater than that of the activation energy, EA. So here's an example. We have two molecules. We have a nitric oxide molecule coming in and colliding with a chlorine molecule. A reaction occurs and the chlorine is transferred, makes a bond with the nitrogen. Okay, so now we have a nitrogen-chlorine bond, and the free chlorine atom flies away. So, and again, we're assuming that it had enough energy for this to occur. Okay, now let's say we have the same two molecules, except this time, instead of the chlorine running into the nitrogen, this time the chlorine bounces into the oxygen. Well, that's going to result in no reaction at all. They're just going to bounce off each other like billiard balls, okay? So they're just going to bounce off each other. So you can see that they have to have so they both had the same amount of energy, but this one just didn't collide properly. It had to hit the nitrogen, not the oxygen. So that's what we mean by proper orientation. Now, this is usually important for neutral compounds. If you have two ions reacting, it doesn't matter as much because the ions will pull each other to one another and eventually get into the correct orientation. Okay, so this is generally more important for neutral compounds than it is ionic compounds in solution. Okay, okay. So again, got to have enough energy and you have to have the proper orientation. Now, the transition state theory talks about a further step, which is called the activated complex. So when these two individual molecules come together, they're going to start to form a bond. So the nitrogen-chlorine bond is going to start to form, right? It's starting to form. And then this chlorine-chlorine bond is starting to break. And if it has enough energy, and this is what we call the activated complex, okay? If it has enough energy, if it doesn't have enough energy, it's going to go back and just fall apart and form the original nitric oxide and molecular chlorine. But if it does have enough energy, it's going to go on to form products, okay? Now I say if it doesn't have enough energy, it's always going to go back. But the reality is even some of those that had enough energy will still go back. And we're actually going to quantify this whole idea, which actually we're just going to say this to our products. We're going to ignore the activated complex in a balanced chemical reaction, right? So we're just going to say this part goes to our products, and we're going to ignore the activated complex part, okay? And we're going to actually quantify this with what we call a rate constant, and then later on, we'll also talk about an equilibrium constant. So we'll be able to determine the concentrations of reactants and products under given conditions. So we're going to find out that kinetics and equilibrium are related to one another, okay? They're inseparable. So there it is again. So the molecules come together with the proper orientation. They form an activated complex. If they have enough energy, they're going to actually form the products. Okay. Now keep in mind this reaction, a free chlorine atom can react with this compound here, okay, nitrosyl chloride, and actually go backwards and form nitric oxide and chlorine. So right now we're just talking about the forward reaction, but the reverse reaction can also occur, okay? So again, the activated complex, also called the transition state, is unstable, so you can't isolate it. So in other words, I can't collect a jar of this activated complex. It's immediately either going to go to products or it's going to fall back apart to its original reactants. Okay, so again, that is our activated complex. Now, let's talk about what a reaction rate is. So here's an example, right? So we have the reaction rate. We have 2 dinitrogen pentoxide molecules reacting with one another to form 4 nitrogen dioxide molecules and 1 oxygen molecule. Now, the reaction rate of a reaction is the increase in molar concentration of product per unit time. Okay? So that's an increase in our products. It's also going to be a decrease in our reactants. So let's just look at that. It's going to be an increase in our products. Now, the reaction rate can be expressed as a decrease in the molecular concentration of the reactants. So in other words, this is going to always increase, so it's positive. And we're always assuming that the reactants are disappearing, going to the products. So that's reaction rate's always going to be negative. Now, we're talking about the individual rates of our reactants and products. We're eventually going to talk about the overall rate of the chemical reaction itself. So again, the individual rates, the products are always increasing, so they're always positive per unit time. And for the reactants, they're always decreasing. We're assuming they're always going from reactant to product, so it's always going to be negative, right, per unit time. So again, we have our decomposition of the dinitrogen pentoxide. Heated up and it occurs faster, right? That's what the delta sign represents. So heated up and it goes faster. And we could represent the change in concentration. Let's say we're looking at just O2. So all we're doing is monitoring the O2 gas. And the change in concentration then is just going to be del. Notice here it's heat, but here it's del, and you just got to understand that. The square brackets mean that it's a molar concentration, okay? So the square brackets means it's a molar concentration. So this is the change in the molar concentration of O2. Now it's per unit time. So the average rate of formation of oxygen is positive because it's a product. We always assume that it's increasing, so this number is always positive, okay? And per unit time. So how did this concentration change over a given amount of time? So this is the average rate of formation of our product, oxygen. Now, as we continue to reduce the amount of time, we go from an average to an instantaneous rate, which we could determine using special instruments, okay? Generally, in the lab, if you're doing it yourself without an instrument, you're actually measuring the change over a given amount of time, like you would do in lab, for example. But if you have sophisticated equipment in your lab, you could actually determine the instantaneous rate by just making this infinitesimally small, okay? Okay, so let's look at what happens here. So here we have a graph of concentration of O2 versus time. So at time 0, we don't have any O2. The only thing in our reaction flask is the dinitrogen pentoxide. So there is the concentration is 0 at time 0. So we're starting out here. And then as the reaction proceeds, the concentration of O2, right, is going to increase. The volume is going to remain constant because the reaction vessel is going to be of a fixed volume. So basically, it's the number of moles of O2 that are increasing. And with time, we can see it increases. Then all of a sudden, it starts to slow down and eventually levels off. And this is because as this is increasing, right, 2 things are occurring. First, the concentration of N2O5 is decreasing, which means there's less and less and less to react. And secondly, the concentration of O2 is increasing. And as we're going to see when we talk about equilibrium, well, there's a point in the chemical reaction when the concentration of the products and the reactants don't change anymore. We call that equilibrium. So during a chemical reaction, the concentration of the reactants and products are going to change, but at some point we reach equilibrium where those concentrations are no longer changing. And so that's why it ends up flattening out. We reach equilibrium. But notice the rate is linear at first, right? It's pretty straight at first, but then all of a sudden starts to slow down as the reaction proceeds to equilibrium, okay? Now, we can actually calculate the average rate. So for example, at this part of the chemical reaction, so about halfway through, to determine the average rate, we just determine a certain amount of change in time, right? So that's del T, so that's about 600 seconds. And then we're going to look at how the concentration of O2 changed, right? So here would be the beginning, and here would be the final, right? The tangent of this point would actually represent the instantaneous rate. So you could actually determine the instantaneous rate if you want to do a little calculus. You could actually find the instantaneous rate at any portion. It's just the tangent of the curve, okay? But for the average rate, again, we would just look at a certain amount of time. So in this case, let's say 600 seconds. So this is the initial rate. This is going to be important. We're going to talk about initial rates a lot. That's where the portion of the rate is basically linear. Okay, so that's our initial rate. So we looked at a 600-second time span, and the concentration went from 0 up to 0.0018. So that ends up being our change in the concentration of O2. So the average rate of formation of O2 is just the change in concentration of O2 with respect to the change in time. So our initial rate then is going to be 3.6 times 10 to the negative 6 moles per liter per second. This is the units of rate, moles per liter per second, okay? That is always our units of rate. Now you can express rate in different units, but we're going to stick with this, okay? Now we could actually determine the average rate later on in a reaction, right? This is our initial rate. This is an important one. This is the one that we would want to measure. But we could measure the rate at some later point stage in the chemical reaction. So here we're talking what, from about 4,200 seconds up to 4,800 seconds, okay? Again, we're going to take that difference, which is 0.0025 moles per liter. And so now we can see that our average rate later on towards the end of the chemical reaction is now only 0.4 times 10 to the negative 6 moles per liter per second. So we can see that the reaction slowed down quite a bit as we got closer to equilibrium, the end of the reaction. So equilibrium is the end of the reaction, okay? Okay, any questions so far?
Wait, calculating the initial rate versus the average rate. Can you explain?
They're both
They're
average.
the same.
They're both average rates. This is the average initial rate. This is the one that we will use all the time when we're trying to figure out later on what we call rate laws. Okay.
Okay.
This is, I'm just showing you, is the average rate at a much later time in the reaction.
Okay, same thing, different story.
They're both average rates. It's just when did we look at it? This was the initial rate.
Mm-hmm.
This was the rate later on in the chemical reaction. This is the one that we're going to be most interested in. But I'm just saying, hey, look, we can calculate the rate at any time. And more importantly, we can see that the rate is slowing down as the chemical reaction comes to an end as it reaches equilibrium.
Okay, that makes sense. Thank you.
Okay, so any species, reactants, or products can be used to express the rate since their amounts are related through the stoichiometry, right? Through the coefficients in the balanced chemical equation. So I know that the average rate of decomposition, so the loss of N2O5, is going to be the change in N2O5 with respect to time. However, rates always are positive values. Let me say that again. Rates are always positive values. But I know that this difference is going to be negative since I'm losing my reactants. So when you're looking at the average rate of the loss of your reactants, you have to put a negative sign in there because the rate always has to be positive. Okay? So again, always positive. That's why we got to put a negative sign there.
Would you be able to determine the rate of decrease based off of the rate of increase of oxygen?
Yeah, I'm going to talk about that in a second because, again, we could relate it through the coefficients of a balanced chemical equation. So that's when we're going to start talking about the rate of the reaction. These are rates of reactants and products. We're actually not so interested in that, but we need to calculate these to actually get the rate of the chemical reaction. We only need one. We only need the one of the rate of disappearance of one of the reactants or the rate of appearance of one of the products, and from any of them, we can get the actual rate of the whole chemical reaction, which I'm going to talk about right now. Okay, so again, we've seen that the rate of O2, again, this is going to be positive because it's going to be increased. That's why there's no negative with respect to time. So that was the rate of appearance of our product. Now, when I compare that to the nitrogen dioxide, well, the nitrogen dioxide is forming four times as fast as the O2, right? So for these two rates to be equal, I'm going to have to divide this by 4. In other words, 1 over the coefficient. Okay? Since this is being produced 4 times faster, I got to divide its rate by 4 so that it's equal to the rate of appearance of O2. So now you can see where these two are related through the coefficients in the balanced chemical equation. Well, I could do the same thing for the loss of the reactants. So there's the rate of change for the loss, right? Again, the negative, because this value would be negative. But we're losing that twice as fast as we're gaining oxygen. So for those two rates to be equal, I have to divide this rate by 2 so that it now equals the rate of appearance of the O2. Okay, any questions about that? Hannah, does that answer your question?
Yeah, it makes sense. Thank you.
Okay, so now any one of these equals the average rate of the chemical reaction. Okay, so the overall rate, we're talking about the rate of the chemical reaction itself, not individual reactants or products, but the overall rate of the chemical reaction, which we're just going to call rate. And we're always going to assume that when we're talking about rate, that we're talking about the rate of the overall equation. But we get it from the individual rates. So here's a generic reaction, right? We have reactant A reacting with reactant B to form product C and product D. And the lowercase letters represents the coefficients of that balanced chemical equation. So we can get the overall rate from any one of them. Where again, since it's the reactants are disappearing, that's why the negative, because these values are negative. So 1 over the coefficient, right? We can see that. When we get to the products, it's positive because these changes are going to be positive. And again, it's just 1 over the coefficient in the balanced chemical equation. So again, we can get the overall rate of reaction from any reactant or product, and we only need one. Okay, so does everybody understand this generic form of the overall rate? Any questions about it? Okay, so let's talk about how we experimentally determine the rate of a reaction. Well, we're going to do this by measuring an individual rate of the reactants and products, okay? And we're going to always do the initial rates. Now, there's a bunch of ways we could do it. We could either monitor the reactants or the products, or we could measure actually the whole thing by just measuring the pressure. So for example, if we have a really slow reaction, we could simply withdraw samples from the reaction vessel and analyze them, determine the concentration of just any reactant or product. Now, if we're looking for the rate law, we need to understand the concentration of the reactants and products, all of them, which we'll talk about here shortly, okay? So a more convenient technique simply involves the continuous monitoring of the reaction. You could do that by looking at the pressure, if it involves gases, if it doesn't involve gases, or the number of gas molecules are the same as in reactants and products, then the pressure will never change. So it has to have gases, and there has to be different number of gas product compared to reactant molecules. You could use conductivity. So if it's an ionic compound and the number of ions are changing within solution, you simply can use the conductivity. The more ions, the more conductive, the less ions, the less conductive. If you have organic molecules, you could look at the absorption. So for example, infrared spectrophotography, you could see a chemical bond. Let's say we have a CO double bond that's forming in a chemical reaction. Then you'll see the absorption of that particular bond increase with time, and you could use that, quantify that, okay, from the IR, and actually use that to determine how the rates are changing, okay? So here's an example. Here we have a chemical reaction in which, again, this is just a decomposition of the dinitrogen pentoxide to form nitrogen oxide, dioxide, and oxygen. Notice there's 2 moles of gas is the reactants, and there's total of 5, 4 here and 1 here. So we're going from 2 moles of gas to 5 moles of gas. So as this reaction proceeds, the pressure is going to increase. So what we're going to do is we're going to take our dinitrogen pentoxide, we're going to put it in a reaction vessel. So there's our flask, and it contains these brownish orange dinitrogen pentoxide gas. Now, remember, we had to heat it. So again, in this case, we're going to heat it to 45 degrees Celsius. So we're going to put it in a water bath that's at 45 degrees Celsius. So that's going to keep this always at 45 degrees Celsius, regardless if the decomposition is exothermic or endothermic. Doesn't matter, because we're going to keep it at 45 degrees Celsius, okay? And if we change the temperature, the rate of how fast it's going to occur is going to change. As we increase the temperature, the reaction is going to occur faster and faster and faster. Okay, so now as the reaction proceeds, I can continuously monitor the pressure of the reaction simply using a manometer, right? So all we're looking at is the difference in height between these two here. So when at atmosphere, when it's at atmospheric pressure, the height is right here. So that's why I don't have to have scales on both sides. So this manometer is only for measuring increases in pressure. So as the pressure increases, right, we see that it increases up, okay? Okay, so now normally the rate of reaction increases when the concentration of reactants is increased, and may also increase when the concentration of the catalyst is increased. Okay. Now notice I said normally. It could have a different effect. As I increase the concentration of a reactant, it could slow or decrease the reaction rate. Okay. But usually it increases it. Now the likelihood of a successful collision between reactants increases as the population of reactants increase, right? So the more, so for example, I always use students in the classroom, right? If I have, let's say, just 4 students in the classroom, I blindfold them and I tell them just to randomly walk around the room, every once in a while they're going to bump into another student. But let's say I quadruple that. I go from 4 students to 16 students in the same room, in the same volume, blindfold them, tell them to walk around randomly. What increase are you going to have into bumping into other students? How's that going to increase? You're all walking at the same speed.
It's should increase, right?
By what factor? If I went from 4 students to 16.
Like, would you just be 4 times more likely to?
Yeah, exactly right. You'd be 4 times more likely to bump in. So that's normally the way the kinetics work. It doesn't always happen that way. Sometimes when you double, let's say we go from 4 to 8 students. Normally that will result in a doubling of the rate. But sometimes that might end up in quadrupling the rate. We'll understand this better when we actually look at the elementary steps. So we're going to find out that the chemical reaction doesn't occur as one step. It occurs as a bunch of individual molecular reactions. So a bunch of individual chemical reactions that we add them all up and we get the overall chemical reaction. That's the one that we normally deal with. We're going to talk about that at the end of this chapter. So tomorrow or Thursday, we'll start talking about that. Okay. And again, by the way, I believe the first exam is next Wednesday. And I believe it's only on 2 chapters. So the last chapter and this chapter that we're dealing with now. So keep in mind, this goes fast. Okay, I'm sorry. Okay, so again, as we increase the number of reactants, the likelihood of successful collisions occur and the rate increases. However, the rate may be unaffected by the concentration of a particular reactant, but simply needs to be present. Okay, so a lot of times we'll see that with catalysts. But it doesn't matter how much catalyst is there, it just needs to be there and the reaction will proceed at the same rate. So if I just add more catalyst, well, so no catalyst at all, the reaction goes slow. Add the catalyst, the reaction speeds up. Add more catalyst and nothing happens. It still stays at that same speed, okay? Okay, so does everybody understand what I'm saying there? So basically, sometimes when you add more reactant or catalyst, the reaction speeds up. Sometimes you add more and nothing happens. Sometimes you add more and it actually becomes slower. We'll talk about all of these different scenarios. Okay. Okay, so here's an example. I have nitrogen dioxide reacting with molecular fluorine to form nitrofluoride. Okay. Now, the rate of this reaction has been observed to be proportional to the concentration of both nitrogen dioxide and molecular fluorine. When the concentration of the nitrogen dioxide is doubled, the rate of the reaction doubles. When the concentration of fluorine is doubled, the reaction rate is doubled. Notice that has nothing to do with the coefficients in the balanced chemical equation. This is for an overall reaction. For an overall reaction, the coefficients mean nothing. When we start talking about elementary steps, those individual molecular events, the coefficients mean everything at that point, okay? But for the overall reaction, the coefficients mean nothing. We have to experimentally determine how the reaction rate is affected by changing the concentration of the reactants. So a rate law then is an equation that relates the rate of a reaction to the concentration of reactants and catalyst raised to various powers. So here's another example. Here is the degradation of hydrogen peroxide into water and gaseous oxygen. This should be a liquid. I changed this slide so it's slightly different than what you see in your notes, by the way. And you're going to see me do that kind of stuff all the time. Okay, so again, we see the decomposition of the hydrogen peroxide to water, which is liquid, and gaseous oxygen. When we add iodide ion to it, sodium iodide, hydroiodic acid, don't care. When you add iodide to this reaction, now notice that I wrote it above the arrow. That means it's a catalyst. So when I add iodide to this reaction, it speeds up But notice that it's not in the reactant or product, okay? So nothing ever happens to it. It just causes this reaction to speed up. Now, as we're going to see later on, that's not quite true. This iodide does react to form something else, but then that something else again reacts to regenerate the iodide itself. So we'll talk about that kind of stuff later. But let's talk about what the rate law is. This would be the rate law. So the rate is equal to this lowercase k. In the next chapter, we're going to talk about equilibrium constants, and that's going to be a capital K. So the rate constant is a lowercase k, and that is what we call a proportionality constant. That proportionality constant allows us to relate it to the concentration of this case of the reactant and the catalyst. And in both cases, the concentration is raised to the first power, which is understood, right? So this is raised to the first, this is raised to the first. And we're not going to write a 1, right? We never write a 1 when we raise it to the first power. So notice that even though this has a coefficient of 2, it is raised to the first, and we're going to call that first order. So again, it has nothing to do with the coefficient. So generically, I could write that like this. So here's the rate law. Now, this is when we're going to do it experimentally. We could see that all we're going to have is the rate is equal to K, the equilibrium constant, times the concentration of our reactants, in this case A and B, and the catalyst, C, if a catalyst is present. And then each are raised to some exponent, X, Y, and Z, which we're going to call orders. If it's 1, it's first order. If it's 2, it's second order. If it's 3, it's third order. If it's 0, it's 0th order. And it doesn't have to be a whole number. It could be 1/2. X could be 1/2. Then it's half order. It could be -1. So it'd be negative first order. That means when you add stuff, the chemical reaction actually slows down. Okay? So again, they're normally integers, but they don't have to be. They're normally positive, but they don't have to be. Okay? Now the reality is that if you're getting really sophisticated, the rate law can contain the products. But we're keeping it simple, and for now we're just going to say reactants and catalyst. But it can contain the products as well. It doesn't normally, by the way. Normally you can get away with just looking at the reactants and catalyst. Okay, so the reaction order with respect to a given reaction species simply equals the sum of the exponents. So the overall reaction order would just be X plus Y plus Z. The individual orders would be, so A would have the X order, B the Yth order, and C the Zth order. Okay? So that's the reaction orders, and then the overall orders is just the sum of X, Y, and Z. So the individual reaction orders, and then the sum is the overall order. Okay, so let's consider the reaction this time of nitric oxide with hydrogen, molecular hydrogen to form molecular nitrogen and water vapor. Okay. The experimentally determined rate law is rate is equal to K, the reaction. Oh Lord, I've lost my mind. The rate constant, okay? So the rate constant, and then we can see the concentration of NO is raised to the second power, which means it's second order, and then the hydrogen is raised to the first power. So again, note, it has nothing to do with the coefficients, okay? So we would say that this thing is second order in NO, first order in hydrogen, and then the sum 2 plus 1 is 3, so it would be third order overall. So does everybody understand that?
Are the orders based off of charges?
The orders are based off of the kinetics, how fast the reaction occurs. I'm going to show you that here in a second, how we experimentally determine these exponents. So basically what this is saying, right? If I doubled the concentration of NO, what's going to happen to the rate?
The rate will double.
No.
Or
So I'd make this a 2. 2 to the 2 is what?
4.
4.
So it's 4 times likely?
It went 4 times as fast.
Oh, okay.
What if I doubled the concentration of H2? I went from 1 to 2. What happens to the rate?
Then it would double.
Then it would double.
Okay.
What if this was a
Good.
3? What if this was a 3 and I went from a concentration of 1 to a concentration of 2? What would happen to the rate if this was a 3, third order?
Then it would triple?
It would triple, which means by a factor of what? What is 2 to the third?
8.
8. So it would increase by
Oh,
times or 8-fold.
okay.
Does that make sense?
So you're looking basically at that equation and not at the actual chemical formula, like, because it says 2NO, so I thought like, oh, if you double, okay.
Again, I
I see how
repeat,
you're, yeah.
it has nothing to do with these coefficients, nothing. Notice this is a 2, but this is a 1. It was just a coincidence that this 2 and this 2, just coincidence. Now
So
that
you
is
look
for
at
the,
the rate.
this is for the overall reaction. We're going to later on talk about how this actually occurred in many steps. We call those individual molecular events the elementary steps. When we start talking about elementary steps, then the coefficients come into play. But for the overall reaction, we got to determine it experimentally, and these coefficients mean nothing for the orders. Okay, these got to be determined experimentally. Okay. Okay, so although reaction orders frequently have whole numbers, again, particularly 1 and 2, very, very, very common. They can be fractional, they can be 0, they can be negative. Now, the concentration of a reactant with 0 order simply has no effect. And it's not going to appear in the rate law. Because what is, let's see, what is 13 raised to the 0th power? This is arithmetic.
13 zeros, 1.
1. What is 483.6 to the 0th power?
Still 1.
1, right? So we're not going to write anything to the 0th power. It's just 1. So it just disappears out of the equation, right? So if it's 0th order, it doesn't appear in the rate law because it's anything raised to the 0 is 1. Now, how do we experimentally determine it? Well, the easiest way is to use what's called method of initial rates. So this is basically where we're just measuring the initial rate of the reaction. That portion of the reaction where the rate was increasing linearly, flat line, okay? Now, basically it involves running the experiment multiple times, and each time varying the concentration of only one of the reactant at a time. Now, there are more sophisticated methods where you can change the concentration of all the reactants at the same time, but that just requires more complicated math. I'll leave that for any of you who deal with kinetics later on in life. That's actually the better way of doing it because it's faster, okay? It's more difficult, but it's faster. But we're going to concentrate on just changing the concentration of one reactant and keeping everything else, all the other reactants, catalysts, constant, and seeing how changing that one reaction affects the initial rate of the reaction. Okay, so this is called the method of initial rates. We're going to find rates in different ways, so you've got to understand when I say solve this using method of initial rates, you need to understand what I'm talking about. Okay, this is why you got to do the homework. Got to do the homework. Okay, so method of initial rates. Now, the resulting change in the rate is going to indicate what the order of that particular reactant is. So, for example, if you double the concentration of a reactant, so you go from a concentration of 1 to 2, You doubled it. This results in doubling the rate. So basically that means that that was raised to the first order, right? Because if I go from 1 to 2, 2 to the first is 2, I doubled the rate. So this is the way you can always think of it. Think of it, your concentration always going from 1 to 2, and how that 2 then will be raised to what power. So if doubling the concentration, again, going from 1 to 2, results in the rate going up by 4, right? Quadrupling the rate. If it goes up by 4, well, 2 to the 2 is 4, so that must be second order. And if you double the concentration of the reactant and the reaction rate increases by 8, so that's going to be 2 to the third would be 8, and therefore that would be 8-fold. Now keep in mind, I'm going to show you a mathematical way of doing this where you don't need to memorize any of this stuff. And in fact, I encourage you to learn the mathematical way, because if it isn't one of these whole numbers, you're not going to be able to answer the question. But I'm just showing you that how it works. Because again, it doesn't have to be a whole number. It could be a fraction. It doesn't have to be positive. It could be negative, or it could be 0th order, right? Again, you increase the concentration of the reactant, or most likely the catalyst, and the rate doesn't change at all. So that means it's 0th order. That particular reactant or catalyst won't even appear in the rate law, because it's going to be raised to the 0, which is just 1. Okay, let's try an example. So again, remember I said that we could use iodine. Well, if we use iodine in an acidic solution, we actually convert, instead of just decomposing the hydrogen peroxide into water and oxygen, if we do it in acidic solution, we actually cause the iodide to form another polyatomic ion, which you don't need to know, okay? But again, the only polyatomic ions you need to know are those that are listed in that table. So in this case, we create a new polyatomic ion called the triiodide anion. Okay, so this would be the chemical reaction for it. Now, let's determine the reaction orders with respect to the 3 reactants, the hydrogen peroxide, the iodide, and the acid, the hydrogen ion. So we're going to run a bunch of experiments, and we're going to change the concentration of each one of these individually as we go along, okay? So here we go. There's our chemical reaction. I ran the experiment where I had the concentration of hydrogen peroxide at 0.01, 0.01 for the iodide, and 0.0005 for the acid. And I measured its initial rate to be 1.15 times 10 to the negative 6th. I ran the experiment again. This time I doubled the concentration of the hydrogen peroxide, but kept the concentration of the iodide and the hydrogen ion constant, measured the rate, and it changed to 2.3 times 10 to the negative 6th. Ran the experiment a third time. This time kept it at the 0.1 of the original, but doubled the concentration of the iodide and kept the hydrogen ion concentration the same, measured the rate, and again, I measured it to be 2.3 times 10 to the negative 6. And then finally in experiment 4, I have the concentration of the hydrogen iodide, the concentration of the hydrogen peroxide is same as the first experiment, iodide same as the first, but this time doubled the concentration of the hydrogen ion, and again measured the rate. Okay, so we ran our experiment, in this case 4 times. That allowed us to change one of the reactants differently for each of our reactants. Okay, okay, so now let's say I want to determine the rate of hydrogen peroxide. What 2 experiments am I going to compare?
1 and 2.
Yeah, 1 and 2, right? So going from 1 to 2, I doubled the concentration, but kept the concentration of everything else the same. They didn't change. Okay, so what happened to the rate when I doubled the concentration of the hydrogen peroxide? What happened to the rate when I doubled the concentration of hydrogen peroxide?
It doubled.
It doubled. So therefore, what is the reaction order then of H2O2?
It would be
1.
twofold.
So I got a 1 and a 2. What is it? What is it?
First order?
It is first order, right? Remember, we go from the concentration of being 1 to the concentration of 2. So always think about that 2, right? And if I double the concentration, but I double the rate, that means the exponent for that 2 had to be 1 because the rate only doubled, right? So in this case, then we doubled the concentration, therefore it's going to be first order, right? It's going to have a exponent of 1, so first order. Okay, now let's say I want to look at the iodide. What 2 experiments am I going to need to look at for the iodide?
Two and three.
Say again? I'm sorry, you just talked over each other and
I think 1 and 3.
1 and 3, everybody agree? Is there any others that you could possibly use? Not really, right? Because in every other combination, so if we look at 1 and 3, this and this is constant, this doubled, this is constant. Any other combination is going to result in more than one thing changing concentration, right? So we have no choice here but to use experiments 1 and 3. Okay, so what happened to the concentration? So let's see, Kaylee, what happened to the concentration of iodide going from experiment 1 to 3?
It doubled.
It doubled. What happened to the reaction rate?
It stayed the same. Or no. It doubled.
It doubled. So what's the reaction order then of iodide?
First order.
First order again, right? Okay, Kayla, what experiments would you use to determine the hydrogen ion order?
One and four.
1 and 4. Okay, because it went from 0.005 to 0.001, but in 1 and 4, that remained the same, that remained the same. Okay. Okay, Kayla, what happened to the concentration of the hydrogen ion going from experiment 1 to 4? You just muted yourself. Hit spacebar again, there you go.
It doubled.
It doubled. What happened to the rate?
It doubled. Oh, wait, no. Oh, it didn't change.
So what's the order then of the hydrogen ion? What did you multiply this number by? What did you multiply this number by to get this number? Now that's stupid.
Oh, so what did it
Well,
just
not
be?
really. What did you multiply it by? What number? What number can I multiply this by to get this number?
You could, can't you just raise it to the 0 power and it'll be 1?
It's going to be the power of 0 because it's going to be 1, right?
Yeah.
We multiplied this by 1 to get that. So that means it was the 0th order. We raised it to the 0th order because that's going to be 1.
Okay.
And not change the rate then, right?
Mm-hmm.
So this then is going to be 0th order because the rate doesn't change. Okay, is everybody comfortable with that? Now, like I said, when I do problems, I'm going to show you a mathematical way of determining the actual orders. Okay, it's actually really easy, and I'll show you how to do that. Okay.
I have a question about where you got these concentrations of 0.010.
Like,
I literally went into the lab and I made solutions with these concentrations. I did the experiment 4 different times, creating different concentrations.
So if we're given like an equation and we have to determine
You
the,
will be given a table that looks just like this. Otherwise, unless of course you have Chem 113, then you're going to go in, well, unfortunately, not now, but you would have gone into lab and you would have literally made solutions of different concentrations. In fact, this is the chemical reaction that you're dealing with in the Chem 113. Okay, and you're going to use starch as an indicator. That's going to take the solution from clear to dark blue. Okay, and you're going to make up solutions of different concentrations, and you're going to measure the rates of each one of them. So you would literally go into the lab. Now, during an exam, I can't send you into the lab, so I'm going to give you the data like you actually collected it. Okay. Okay, so putting that all together then, this is what our rate law would look like. Rate equals K, that rate constant, times the concentration of hydrogen peroxide, which we determined was first order, so coefficient of the exponent of 1, which we don't write. The iodide was first order, so it's raised to the first, which again, we don't write the 1. Then the concentration of the hydrogen ion, that was 0. But of course, anything raised to the 0 is 1, so that's why it doesn't appear in the rate law. So this is our rate law. The rate law is a mathematical equation that relates the rate of reaction, moles per liter per second, to the concentration of reactants, catalyst, and sometimes products. Okay? And don't forget to put K. When I ask you to write the rate law, don't forget to throw that K in there. It's got to be there. Every rate law has its own individual K. In other words, every chemical reaction has its own K value. And on top of that, it's temperature dependent. So that K changes with temperature. Okay? Okay, any questions about how to get a rate law?
I had a question about specifics in the sense of, can you, when you're doing this, like you have your chart, it's only reactants with reactants and products with products?
What?
That's it. Like,
In this case,
is
you're
this
only
just for
given
reactants?
this method. Yes, this is only for reactants. Now, like I said, there are more complicated chemical reactions where you would have to take into account the products. We're not going to do that. We're going to keep with the simple ones and just use reactants. Okay?
Okay.
So if you take a higher level chem, you're going to start dealing with that. That's all chemistry is. It's everything you learned in Gen Chem, basically, and we just make it more and more and more complicated, more and more realistic. Okay? Okay, so again, it's first order in hydrogen peroxide, first order in iodide, 0th order in hydrogen. Then the overall rate is simply the addition of these exponents. Well, 1 plus 1 is equal to 2. So overall, this reaction is second order. Overall. So we have individual orders of reactants and catalyst. And then the overall reaction order is just the sum of those exponents. 1 plus 1 is equal to 2. So it's second order overall. It's that simple. Don't make it complicated. Okay, now that we have the rate law, right? So now that we have the rate law and we've run a bunch of different experiments, I can now determine what the rate constant is, right? I just need to choose any one of these experiments, and it does not matter which one you choose. You're going to get the same value of K. You better. Now, in reality, for those of you going into the lab, you're going to get Ks that are very close to one another. They're not, they should be very close. If they're not, you probably did something wrong somewhere along the line. They're not going to be identical, but they're going to be really close. Then in the end, all you do is you take the average to find out what your K is. But for the homework problems I'm giving you, the Ks are going to be identical. So I'm giving you really good data, okay? So the K is going to be the same no matter which experiment you choose, because all you're going to do to find K is plug in the rate, which was given to you, the concentration of the H2O2, which was given to you, the concentration of the iodine, which was given to you. In this case, since the hydrogen ion is 0th order, we don't even care what it is. So we're going to use any one of those experiments now to determine what the rate constant is. So let's just use experiment 1. But again, you could have used 2, 3, or 4. So there's our rate law. We could rearrange it, or let's just plug in, right? So the rate was 1.15 times 10 to the negative 6 moles per liter per second. The concentration of H2O2 was 0.010 moles per liter. The concentration of the iodide was 0.010 moles per liter. Okay? So let's rearrange it. All I did was divide both sides by this, right? And when you divide, you multiply them by the inverse. So when it goes from this side to this side of the equal sign, you just flip numerator and denominator. So you can see that's all I did here. Now this is important that you can do this stuff because you are going to be responsible for units. So now that it's written like this, the units are pretty easy, right? I can see a mole canceling a mole and a liter canceling a liter. Now what I'm left with is a liter per second per mole. So that's the units of this particular rate constant for this chemical reaction, which it's not here anymore, but for this particular chemical reaction, this rate constant has units of liters per second per mole. Plug it all in and you get 1.2 times 10 to the negative 2 liters per second per mole. Now you're going to find out for an overall second order reaction, this is always the units of K. But if it's an overall first order reaction, the units of K are different. If it's a third order overall reaction, the units again are going to be different. Okay, any questions on determining the value of K, the rate constant? Yeah, there's quite a few equations for this chapter. And so the first one is just a general idea, right? If you have a reaction and you want to relate the rates of the different reactants and products, so for very simply, let's say we just have a reaction A going to B, where A and B are the coefficients in the balanced chemical equation. And if we want to relate those rates, well, we know the rate. Okay, so rate in this case, the word rate is actually our variable. Sometimes it's written as R or capital R, but usually I just write it out as rate, but that is actually the variable for rate. And of course, we talk about rate, we talk about the change in concentration of either the reactants or the products with respect to time. So we're talking about the change. And again, the square bracket means the molar concentration of A changing. Now, we always assume that the reaction is proceeding in the forward direction. So that means that this change has to be negative, but rate always has to be positive. So we're going to end up putting a negative sign in front of this thing, okay? And then, like I said, that's with respect of time, so that's just the change in time. Now, this is the average rate of disappearance of A. But if we want the overall rate, then we have to divide that by the coefficient in the balanced chemical equation. So now this represents the overall rate, right? So the individual rate would have been this. So make sure you distinguish between the individual rates and the overall rates. And generally, we're interested in the overall rates, okay? Now we could also relate this to the products. Again, it would be the change of the concentration of the products with respect to time. Now this case, we're gaining products, so this is going to be a positive number, so we don't need the negative in front. But again, if we want to make it the overall rate, we have to put it 1 over the coefficient in the balanced chemical equation. Okay, so that's just how we get the average rates. Now, one of the other things we're going to be doing is determining the rate law from the initial rates. And that's actually a whole process. There's no equations to go with it. Well, there's kind of one equation, which we'll talk about how we actually calculate the orders of each reactant. But then when we're talking about the time integration equation, so now we could relate the concentration change to a specific time. We have a whole set of those, and it's always for the same type of reaction. It's always just for a single reactant going to however many products. Okay, like I said, if we start adding more reactants, the equations become really challenging. Okay, so we're going to talk about different orders of equations. We're going to talk about the rate law associated with each of those orders. We're going to talk about the integrated rate law or time concentration equation. Again, you can call this the time concentration equation. And we'll talk about the half-life for each of these. Okay. Okay, so we're going to talk about zeroth order reactions, which we haven't talked about yet. We'll talk about that later on today. And if you have a zeroth order and there's only the one reactant, well, remember the rate law is going to be rate. So let's do first order, right? Because we've already looked at first order. So if we have a first order reaction, the rate law is going to be rate is equal to some proportionality constant K, lowercase k, and then the concentration of that reactant raised to the first power. So there would be the rate law for a first order reaction. It's always going to look like that. Now, if we have the rate law of the zeroth order equation, again, it's going to be rate is equal to K, and then it's going to be A raised to the 0. But of course, anything raised to the 0 is 1. So there's your rate law for a zeroth order equation. Doesn't even involve the reactants at all. Because remember, if you have a zeroth order reaction or reactant, no matter how the concentration changes, it doesn't affect the rate. And then we have a second order. We're going to talk about second order reactions because first and second order reactions really make up the majority of all chemical reactions. Okay. And so the rate is going to again equal K times the concentration of our reactant, but this time raised to the second power. So really, you don't need to memorize these equations. You just need to understand what it means to be zeroth, first, and second order, or any other order for that matter. Then our integrated rate law. So we've showed already, I showed how we integrated this rate law with using the change, right? We said that this rate is actually equal to this rate. And then we integrated for an infinitesimally small change in time, which gave us the integrated rate law, which was just the ln of the concentration of our reactant at some time t divided by the concentration that it initially was at time 0. And that was equal to negative kt. And then we said the half-life, well, that's just when half of the reactants, the initial concentration of the reactants is gone. So that'd be 1/2 that initial amount. We replaced this with 1/2 that initial amount. So that gave us 1/2. The ln of 1/2 is negative 0.693. And then that becomes T1/2. And so T1/2 then was simply equal to 0.693 over K. The negatives canceled because the ln of 1/2 was negative 0.693. Well, we're going to do the same thing here. And when you integrate this, you simply come up with the concentration at some time t is simply going to be equal to negative kt plus the initial concentration. And replacing this again with 1/2 of A naught and rearranging would give us a half-life equation then of the initial concentration divided by 2 times the rate constant. And then doing the same thing again for this, using the rate, the rate of the individual component, we get 1 over the concentration of time at some time t is going to be equal to kt. Now notice both of these are negative kt's. And then this is a positive kt. So that's something when you're memorizing these equations to look at. These are both negative kt's and this is a positive kt. And that's going to be, I'm sorry, then we're going to add to that 1 over the initial concentration. Okay. And then again, what we're going to do is we're going to replace this with 1/2 A naught and then solve for T, which then will become T 1/2. And that's simply going to be then equal to 1 over the rate constant time over the initial concentration. So there's all the time concentration equations that you're going to need to know. Another thing that you need to know is that all nuclear decay reactions are first order. Okay, all nuclear decay reactions are first order, and we're actually going to, so all nuclear decay is going to be first order, right? But we're going to replace these concentrations with the actual number of nuclei, and we're going to talk about that as soon as I'm done going over some of these homework problems. Also, we're going to find out that we could determine the enthalpy from the activation energy. Now remember, we said that a reaction could actually go from reactants to products, which we would call a forward reaction. But the products can always go back to the initial reactants, which we would call a reverse. And that has its own activation energy. And the difference between these two is actually equal to the enthalpy of a reaction. Then we're going to talk about where K comes from. What is K dependent on? Can we actually calculate K in some other way? And it turns out we can. We have this equation here. Now, I'm not going to get into the details. I'll go through what each one of these values are. We've already seen what the activation energy is. This just ends up being the molar gas constant, and that's going to be the 8.3145 joules per Kelvin per mole. This is going to be the absolute temperature, so the temperature in Kelvin. And then we'll talk about this A, which is called the frequency factor or the pre-exponential factor. And we'll talk about where that comes from. And this actually is called the Arrhenius equation. So that's the Arrhenius equation. Then we're going to actually use a modified Arrhenius equation, and I'll show you how we derive it, but it's just basically coming from here. And that modified Arrhenius equation simply says the ln of K2, so this is the rate constant at one temperature. This would be a rate constant at another temperature, is going to be equal to EA over R 1 over T1 minus 1 over T2. You'll notice that it looks very, very similar to the Clausius-Clapeyron equation, where we were able to relate vapor pressures at different temperatures. Okay, but this is the Arrhenius equation. It's relating rate constants at different temperatures. And then finally, we're going to need to learn how to use elementary reactions to determine rate laws as well. Again, there's no real equations to go with that. That, again, is just a process that we're going to have to go through. Okay, so that is all of the equations that we're going to need for this chapter. So let's start trying some of the actual problems themselves. So it says hydrogen fluoride can be produced from the reaction of gaseous hydrogen and fluorine, okay, to produce our hydrogen fluoride. The rate of formation of hydrogen fluoride, it says relate the rate of formation of hydrogen fluoride to the rate of disappearance of fluorine gas. Okay, so we want to, the formation of hydrogen fluoride. So the formation of hydrogen fluoride, so that individual rate would be the change in concentration of hydrogen fluoride with time. Okay, so this is going to be the individual rate. Okay, and then we could get the individual rate of, so we want to relate that to fluorine gas. So that's going to be the change in fluorine gas with respect to time. But again, remember, this is going to be negative, and whether it's an overall or individual rate, it has to be positive, so we have to throw that negative sign in front. And then to relate the two, well, I can see that hydrogen fluoride gas is being produced twice as fast as fluorine gas is being lost. So that means I'd have to divide this by 2 so that these two rates equal. And so that's what we'll do. We'll say that 1/2 the change in rate of the the formation of HF is going to be equal to negative the individual rate of disappearance of fluorine. And again, remember, really, this is 1/1, right? Because it's just 1 over the coefficient, but 1/1 is 1, and we're not going to write 1 because it's understood. So this ends up being the overall rate. Okay. Any questions about any of that? Okay, let's try another then. So this says that iodide is oxidized, okay, to iodine. So this is the iodide, right? This is K plus, I minus, it's an ionic compound, to iodide, which is molecular, right? It says it is oxidized, so it's going from an oxidation state of -1 to 0, again, as you recall from Chem 110, okay? So it's going from -1 to 0, its oxidation number increased, and therefore it was oxidized. In an aqueous solution of iron 3 chloride. It says the initial concentration of iron 3. Well, I don't see iron 3 in this. And this, again, this is going to be really important in Chem 112, being able to go from molecular to complete ionic and finally net ionic. We're generally going to work from the net ionic equations and not the molecular. This is the molecular equation. Everything's neutral. Notice in a molecular equation, there's never any ions. That's why we call it a molecular equation. But if we want to go from the molecular equation to the complete ionic equation, remember the complete ionic equation is what's really going on in those solutions before and after the reaction. So we could assume that we have 2 beakers, right? We have a beaker of potassium iodide and a beaker of iron 3 chloride. What happens to potassium iodide when I throw it in water?
It dissociates.
Yeah, why? Can you tell me why it dissociates?
Well, it's an ionic compound, and is potassium group 1A?
It is group 1A.
So everything's going to dissociate with no exceptions.
Right. Again, you need to know your solubility rules. You need to know how to go from the molecular to complete ionic to net ionic equations. Okay. We don't have time to relearn Chem 110. And again, we know from the solubility rules that any salt, now this is a salt, right? How do we know it's a salt? Well, it's first off, it's ionic. So again, naming compounds is really important because you're going to ask the same questions. Whenever you're naming a compound, the first question you ask yourself, is it ionic or molecular? In this case, we have a metal. We have a metal and a non-metal. So we know it's ionic. If it's ionic, it could be one of 4 types of compounds, right? If it's ionic, it could be one of 4 types of compounds. It could be an acid. Now, this could be ionic or a molecular compound. Now, in the case of molecular compounds, the only molecular compounds that are really ionic, and there are exceptions to this, are the acids, the carboxylic acids, right? So this is acetic acid, it's a carboxylic acid, but acids we would consider ionic. Well, that's not ionic, that's not an acid, right? There's no H's even, okay? And generally, we're going to write the H's out front. We're going to get away from that. You're going to start to learn to recognize acids without putting the H out in front. But we can see there's no H out in front. It's not a hydroxide. So there's no OHs here, so it's not a hydroxide. A metal oxide consists of just a metal and oxygen, no other nonmetals. Well, that doesn't contain any oxygen at all, so it's not a metal oxide. Therefore, it is a salt. It's not one of the other three, okay? It's not one of the other three, and therefore it's a salt. So that's how we know it's a salt, okay? So, now, according to the solubility, aqueous, by the way, does not mean strong electrolyte. Aqueous simply means it dissolves in water. Sugar dissolves in water, it's aqueous. All acids dissolve in water. Therefore, they're all aqueous. But we only dissociate strong electrolytes going from the molecular to complete ionic equation. For the acids, we know they're strong electrolytes only if they're one of the 6 strong acids. The hydroxides, well, we know they're strong electrolytes if they're one of the 6 strong bases. Metal oxides are generally insoluble, but we're not going to really deal with them. And then finally, we have the salts. Well, whether a salt is a strong electrolyte or a weak electrolyte depends on the solubility rules. Soluble salts are strong electrolytes and have a phase label of aqueous. Again, aqueous does not mean strong electrolyte except for salts. Or they're insoluble, so they're solids. And solids, liquids, and gases are never strong electrolytes. They're either weak or non-electrolytes. So we have a soluble salt. Therefore, this thing is a strong electrolyte. It's going to dissociate into 2 potassium ions and 2 iodide ions. Okay. What about the iron 3 chloride? Is that a strong electrolyte? Do we dissociate it? Again, why, Keenan?
If you look at the solubility rules, most chlorines are soluble and the iron is not part of that exception.
Exactly, right? The rule actually states, this would be rule number 3, and you don't need to know the rules by their numbers, but rule number 3 tells us that most salts that contain the chloride, bromide, or iodide anions are generally soluble. The exceptions are any compound of the chloride, bromide, or iodide that contain the silver, mercury, or lead ions. Well, iron is not one of those exceptions. It's not silver, mercury, or lead. So iron 3 chloride is a soluble salt and therefore a strong electrolyte. Okay, so we're going to show it as being dissociated. So that's going to give us 2 iron 3s. And then there's 3 chlorides in each iron 3, but there's 2 of them. So that's going to be 6 chlorides. Okay, then we're going to go to the products. Will I dissociate I2? Well, let's name it. Is I2 ionic or molecular? Hannah, is I2 ionic or molecular?
Molecular.
Yeah, right. Now, most molecular compounds are non-electrolytes. The exceptions would be the acids, the carboxylic acids. And actually, we're going to find out that neutral molecular compounds that have nitrogen can actually act as bases. But in this case, it doesn't meet any, it's not going to be an acid or a base. And so again, molecular compounds are not strong electrolytes. So we're just going to write I2 aqueous. Okay. What do you think about the, Taylor, what do you think about iron 2 chloride? Is it a strong electrolyte?
Yes.
Yeah, right. We just went over those rules. Any salt, so it's not, it's a metal and a non-metal. It's not an acid, no H's, not a hydroxide, no OHs. It's not a metal oxide, doesn't even contain oxygen. Therefore, it's a salt. According to the solubility rules, rule number 3 tells us that salts that contain the chloride, bromide, or iodide are generally soluble, with the exception of silver, mercury, and lead. That's not an exception. Therefore, the iron 2 chloride is soluble. So there'll be 2 iron 2s. and there will be 4 chlorides. And then what about the potassium chloride, Leah? Is that going to be a strong electrolyte?
Yes.
Why?
Potassium is a group 1A.
Yep.
Yeah.
Again, right? Is it ionic
Number 1.
molecular? It's ionic because it's a metal and a non-metal. According to rule number 1 of the solubility rules, any salt that contains the group 1A, right? So the group 1A metals or ammonium, NH4+, are going to be soluble without exception. So therefore, we know that that is a soluble salt, thus a strong electrolyte. So it's going to be the 2 potassium ions and the 2 chloride ions. Okay. Okay, now so this is what it really looks like, right? We had this first beaker. We had that first beaker, and then we had this beaker here. And when we mixed them together, we had that. And that's what's literally in the beakers. So the net ionic equation then, we're going to cancel out anything that didn't change going from reactants to products. So did the potassium ions change going from reactant to product? Eugenie, what do you think? Did the potassium ion change going from the reactants to the products?
No.
No, right? I have K plus aqueous, which means this is a potassium ion floating around in solution all by itself. Over here, I have the potassium ion, again, floating around all by itself. It's identical on both sides. There's 2 on this side, there's 2 on this side, so these 2 are going to cancel these 2. What about the iodide, Eugenie? Do you think, did that change at all?
Yeah.
Yeah, right. It's I2 minus over here, an individual ion floating around all by itself. But now all of a sudden it's part of this molecule, this I2 molecule. That's not the same. What about the iron 3 ion? You're on a roll, Eugenie. Go ahead. Same or different?
Different.
Why is it different?
The 3+ and 2+.
Yeah, right. It actually went from 3+ to 2+. It was reduced. They are not the same, so they don't cancel. And then finally, what about the chloride? Same or different?
They're the same.
They're again the same. We got free-floating chloride ions, right? Just floating around in solution. I can't do my math, apparently. That's not true. So again, we have a total of 4 here and 2 here. That's 6. And there's 6 over here. So all 6 on both sides are going to cancel. Later on, we're going to find out that not necessarily all of them cancel, right? Maybe 2 of them cancel on this side, and there's 4 on this side, and only 2 of them will cancel, right? We'll get to that stuff later on. Okay, so now those were what we called spectator ions. They didn't do anything. What's left is the actual chemistry that occurred. So our 2 iodide ions, right? Plus our 2 Fe3+ ions. And they formed our I2 aqueous and the 2 iron 2+ ions. Okay, so there's our net ionic equation. Any questions about that? Going from molecular complete ionic to net ionic. Okay. Okay, so now let's come back to the question, right? So now the question says the initial concentration of iron 3. So now I see the iron 3. So the initial concentration of iron 3, and I could write that like this, right? So that naught means it's the initial concentration at time 0 was equal to 0.5990 molar. Then it says after 10 minutes, it dropped to this concentration. So in other words, the iron 3+ after 10 minutes, dropped to 0.4101 molar. It's asked you to write the complete ionic and net ionic equations, which we already did. This was the molecular equation. And if the molecular equation is balanced, and if you're doing everything right, you don't need to rebalance, but that's one way to check and see if you're doing everything right. It should, if this is balanced, it should remain balanced throughout. Okay. Then it says, what is the average rate of reaction of iron 3 in this time interval? Well, if we want the average rate, okay, well, we know that the average rate, so first off, iron 3 is a reactant, right? So we know that this change in concentration of iron 3 is going to be negative. So we got to put a negative sign out front, right? So this is the average rate of reaction of iron 3 chloride. And again, remember, it's saying iron 3 chloride, but the iron 3 is coming from the iron 3 chloride here. So you could put iron 3 here, or you could put iron 3 chloride here. It doesn't really matter because they mean the same thing, okay? So then that's just the final minus initial, right? So this is just going to be the concentration at some time t minus the initial concentration. And that's going to be the time. So this is just going to be the time final minus the time initial. And so that's going to be the iron at sometime t, which is our 10 minutes, is going to be 0.4101 molar. The initial at time 0 was 0.5990. And then our final time was 10 minutes. And our initial time was 0 minutes. And we're going to consider the 0 to be exact, right? And all of our uncertainty is going to be in the actual 10 minutes. Okay. So basically what we're going to get then is you plug that into your calculator and you're going to get a value of, so this is negative, and then this is going to be negative 0.1889 molar. Now this is, we're subtracting, so it's the significant number of decimal places. So there's 1, 2, 3, 4 here, 1, 2, 3, 4 here. So it'll be 1, 2, 3, 4, okay? And then again, like I said, the 0 minutes is going to be exact, so it's just going to be 10 minutes. Plug that into your calculator, and you are going to get 0.01889 molar per minute. And again, that would be so we have 4 sig figs, so this will be 4 sig figs. Again, remember, zeros in front of a non-zero number are always significant. Zeros to the right of a non-zero number are significant if there's a decimal place anywhere in the number. Okay? Okay, so, and again, we could actually write that. So what did it say? Now, once it's specifically in units of moles per liter per second. Right now, we have basically what we have is 0.01889. Remember, molarity is moles per liter, and this is per minute. So to get rid of those minutes, we're just going to say, hey, look, in 1 minute, there's 60 seconds. So now the minutes cancel, and I'm going to get the units of seconds that I want. And so this is going to be 0.0031483 moles per liter per second. And this is the 4 sig figs, and this would be considered exact. So 1, 2, 3, 4. And so this then would be equal to 3.414, I'm sorry, 3.148 times 10 to the negative 1, 2, 3, 4. And the units again would be moles per liter per second. Okay. Any questions with that? Okay, now that was the individual rate. What about the overall rate? Well, remember the overall rate is just going to equal the individual rate. So this was negative, the change in the concentration of Fe3 plus over del T, which we know is this value. But if it's the overall rate, we got to go 1 over the coefficient. 1 over the coefficient, in this case, the coefficient was 2. So the overall rate then is going to be 1/2 of this number. So it's going to be 1/2 of the 0.000314833. Again, we're not going to use the rounded value. We will use the unrounded value, moles per liter per second. And that's going to give you a value of 1.57416 times 10 to the negative 4. And this is exact. So this is 4 sig fig. So there's 4. And so this then is going to equal 1.574 times 10 to the negative 4 moles per liter per second. Okay. Any questions about the individual average individual rates and average overall rate? Okay, let us try another one then. Again, remember you could always go back to the recording and get anything that you miss. Okay, so next, whenever you see a problem like this, you should know it's going to be the method of initial rates. Okay, so this is the method of initial rates where we're running a bunch of experiments at different concentrations. Okay, so number 14 says the hypoiodide ion, okay, can be produced by oxidizing the iodide ion with hypochlorite ion in basic solution. So in this case, the hydroxide written above the arrow means that it's a catalyst. Okay. So that's the catalyst. So it says we perform a series of reactions, again, changing concentrations of some of them as we go along. And so our first now is to determine the rate law for this reaction. Now remember what the rate law is, right? The rate law that we're looking for is going to be rate equals our rate constant, lowercase k, time to concentration of our reactants. In this case, it is the iodide, right? And it's raised to some power, and that's what we're looking for. The hypochlorite ion concentration, again, raised to some power. And then finally, our catalyst as well. So our catalyst, and again, raised to some power. So to determine the rate law, okay, so to determine the rate law, which is this, we need to figure out what X, Y, and Z are. So let's start with iodide. What two reactions do you think what two reactions do you think we're going to need to use to determine the iodide?
Reactions 2 and 3.
So reactions 2 and 3.
Mm-hmm.
So why 2 and 3?
The iodide concentration is different while the hypochlorite and hydroxide are the same.
Exactly right. So we can see from reaction 2 and 3, we doubled the concentration of the iodide, but the concentration of the hypochlorite didn't change, nor the hydroxide. So we're going to use experiments 2 or 3. And I'm going to do it so that we're putting experiment 3 over 2, and I'll show you why, right? If we look at the rates, I could look at it this way, right? I have the rate of experiment 3 is equal to K. Now, if these experiments are run at the same temperature, okay? If they're run at the same temperature, that means same K values, okay? So same temperature means we have the same K. So then it's going to be the concentration of the iodide for experiment 3, the concentration of the hypochlorite for experiment 3, and the concentration of the hydroxide for experiment 3. And I could do the same thing for experiment 2, right? So the rate of experiment 2 is equal to K. Again, the Ks are the same since it's at the same temperature, but the concentrations have changed. Now the powers aren't going to change, so they'll still remain as X, Y, and Z. Whoops, it's experiment 2, okay? And what I'm going to do is I'm just going to divide these two. I'm just going to divide them. Now, since the Ks are the same, the Ks disappear. So now what I'm going to do is I'm going to say, okay, rate 3 over, well, let me actually put in the numbers, right? Because we got rate 3. So rate 3, that's this number here, 1.18 times 10 to the negative 1. And I could see that the units are going to cancel, right? Does everybody see that? Because each one of these always have the same units. They're always going to cancel. So that's why I'm going to ignore the units here. Because again, we can see that they're always going to cancel. Because this got to be the same as this. So no matter how they affect the units inside the parentheses, they're still going to be the same. Okay? So that's the experiment 1 rate 3. So experiment 1, there's the rate. I'm sorry, experiment 3, there's the rate. Okay. Then we had the rate of 2. So that was the 5.88 times 10 to the negative 2. Okay. It might be easier to think of this as to the negative 1. And if it was negative 1, what would I write this as? You got to get comfortable with scientific notation.
That'd just be 58.8.
Nope, just the other opposite.
The opposite.
Yeah, it's going to be 0.588 times 10 to the negative 1. Remember, we just added 1 to this, and when you add 1, you got to move the decimal point to the left. Okay? Because that now makes it easier, right? Can anybody tell me what this number is? Shouldn't need a calculator. It's just 2. Okay. So 1.18 divided by 0.59 basically is 2. Okay. But anyway, okay, so that's going to equal then, we have this first one. So the iodine for experiment 3, which is 0.03. The iodine for experiment 2, which is 0.015. This is all going to be raised to the x, right? So properties, if I do that, right, I could then raise these all to the x. So that's why that became like that. Then I could look at the next one, right? So the next one was the hypochlorite. So the hypochlorite for experiment 3 was 0.02. And for experiment 2, it was 0.02. That's raised to the y. And then finally, the hydroxide for experiment 3, it is 0.005. And for experiment 2, it was 0.005. And so that's the z. Well, this is just 1, right? So these cancel, and this is just 1. So this whole thing becomes 1. Same thing here. These cancel, so this whole thing becomes 1. Well, 1 times any number is going to be the number itself, so we could just ignore those 1s, right? They basically just cancel out. So now all I have to do is look at this. So we've already established that this divided by this is equal to 2. What about 0.03 divided by 0.015? What's that number? Again, you really shouldn't need your calculator.
Is that just 2?
It's just 2 as well, right? So that's just 2 raised to the x. So what is x?
X is 1.
Yeah, right? 2 raised to the 1 is 2. So therefore, x equals 1. So now we know x. X is 1. And we're basically going to use this idea again, where as long as we keep the concentrations of everything else constant, we know that we could ignore those ones that are constant. Then we could just compare the rates of the 2 experiments and the concentrations of the things that we're interested in. So if I'm looking at the hypochlorite ion, what two experiments do I want to choose to determine why? Jada, what do you think? I want to determine why. What 2 experiments am I going to choose?
You're gonna choose. Give me 1 second. Would you choose 1 and 2?
Okay, 1 and 2. So for 1 and 2, this is changing. This is remaining the same, and this is remaining the same. So yeah, we're going to use 1 and 2, right? So we're going to now use 1 and 2. So again, it's going to be the rate. And I'm always going to put the higher concentration on top. So it's going to be the rate of 1 over the rate of 2 is going to be equal to the concentration of the hypochlorite for 1 over the concentration of hypochlorite for experiment 2 raised to the y. So now I don't need to write all of this anymore. Does everybody understand why I just wrote this? Okay, again, the k's would have canceled. This ratio would cancel because, again, we use the same concentrations. This would have canceled because, again, we use the same concentrations. So the only thing that was changing was these 2. So now we plug in those values. So the rate of 1 is 1.18 times 10 to the negative 1. The rate of 2 was 5.88, which again, we just showed that we could write that as 0.588 times 10 to the negative 1. And this way you don't need to use your calculators. You really don't need to use your calculators, is equal to the concentration of the hypochlorite of 1, which is 0.04. And the concentration of the hypochlorite in experiment 2, which is 0.02. And again, this would be raised to the y. We've already seen that 1.18 divided by 0.588 or 59 is just equal to 2. Okay. And what is 0.04 divided by 0.02?
Isn't it just 2?
It's just 2 again, right? So 2 to the y. And so, Kayla, what is y?
Y is 1.
It's just 1 again, right? 2 to the 1 is 2. So y is equal to 1. And now we have to find z. So, Caitlin, what 2 experiments am I going to use to find the z for the hydroxide?
Two and 4.
Okay, so 2 and 4. So in 2 and 4, the iodide isn't changing and the hypochlorite isn't changing, but we doubled the hydroxide. Now I'm going to put the hydroxide on top, Okay, so that's going to be experiment 4 over 2, right? So 4 over 2. So it's going to be the rate of 4 over the rate of 2 is equal to the hydroxide ion concentration of 4 over the hydroxide ion concentration of 2 raised to the Z.
Wait, can you explain why you put 4 over 2 this time?
Because I'm looking ahead of, right? And I can see experiment 2, the concentration is higher than experiment 4, the concentration is higher than in experiment 2.
So look at the concentrations rather than the rates.
Either one. And honestly, it does not matter as long as you are comfortable with fractions and exponents. If you're not comfortable with fractions and exponents, you're going to want to make sure that you're dealing with whole numbers. Now, I will tell you, as you're going to see, you can't always get away from it. You're going to have to deal with fractions and exponents, okay? But sometimes you can avoid it, and I usually do that by simply putting a higher concentration on top and the lower concentration on the bottom. Or you can put the higher rate on top and the lower rate on the bottom. It doesn't matter, whichever you choose, okay? Again, I generally don't care how you solve problems as long as it's correct and it makes sense. Okay, so then the rate of 4 was 2.94 times 10 to the negative 2. The rate of 2 was 5.88 times 10 to the negative 2. Now they're both 10 to the negative 2. So again, we could just cancel, we could just ignore them and just look at the numbers. And so then that is equal to the concentration of 4, which is 0.0100, and the concentration of 2, which is 0.005. Again, the units are going to cancel, so I'm ignoring them. And that gives me Z. So what is 2.94 divided by 5.88?
2.
Say again?
1/2.
1/2, right? It's actually 1/2 this time. And what about 0.01 divided by 0.005? Michael, what's 0.01 divided by 0.005?
It's 2.
That is just 2. Therefore, what's Z?
At 2.
Nope.
My
2
bad.
to the 2 would be 4.
My bad. That's the 1/2 then.
1/2?
-1?
It's going to be -1, right? Z is going to be -1. If this was 1/2, that would be the square root of 2. The square root of 2 does not equal 1/2.
Sorry, it's too early, man.
Yeah, I understand that. So this is -1, right? Remember what negative means. It means basically that we just take the inverse, right? If I have 2 to the -1, that simply means I have 1 over 2. If I have 1.63 to the -1, that just means I have 1 over 1.63. Okay? So don't be afraid of the negatives. That's all they mean, is you're just taking the inverse of it. Okay? Okay, so now we have the rate law. So the rate law is now rate is equal to our lowercase k times the concentration of the iodide. That's raised to the first, so I won't even put anything. The hypochlorite ion raised to the first, and then the hydroxide raised to the -1. Now you could also write that like this, and again, I don't care which way you write it. They both mean the same thing, right? So they both mean the same thing. So however you're more comfortable writing it. But that is, we just answered the question. That was the rate law for this reaction. Don't forget that K. You don't need to put this is the equation, so don't be putting values in for these things either, right? This is the actual equation. Okay, any questions with the method of initial rates? Everybody good with that? Okay. Now, the next part of this question says, Determine the value of the rate constant. So how am I going to determine the value of the rate constant at this temperature? What would I do?
You'd solve the rate equation for the constant. which
Okay, keep going.
K equals rate.
Okay, so I'm going to rearrange that, right? I'm going to say K equals rate. I'll bring this to the numerator, and I'll divide it by the iodide, and the hypochlorite. Like that?
Yeah.
Okay, now what?
Plug in the numbers for one experiment and then calculate.
Okay, does it matter which one I use?
No.
Not at all. Now, it does matter to me because I only have the solutions for experiment 1. Let me make sure that's true. Yeah, so I'm going to use experiment 1. So, so then basically the rate of experiment 1 was 1.18 times 10 to the negative 1 moles per liter per second. The concentration of the hydroxide for experiment 1 was 0.005. Remember, the molar means moles per liter, so moles per liter. Now that's just raised to the 1. If this was a second order, right, would raise it to 2. And then we have the concentration of the iodide, so that's 0.01 moles per liter. And the concentration of the hypochlorite, which is 0.04 moles per liter. As far as units are concerned, I have moles canceling a mole, another mole canceling another mole. I have a per liter canceling a per liter, another per liter canceling another per liter, and I have units of per second. So plug that into your calculator, and you're going to get 0.9833 per second. I have 3 sig figs, 2 sig figs, 2 sig figs, 2 sig figs, so this will be 2 sig figs. So your final answer will be 0.98 per second. Okay. Any questions about that?
If we use the capital M to signify mole over liter, that'd be fine to cancel out as well.
Absolutely, right? Absolutely. So this would be the mole over liter is big M, mole over liter, big M, mole over liter, big M, mole over liter, big M.
Could you, oh, sorry.
Say again?
Could you also use the equation without the fraction, like that second one you have up there, to solve
This one
for?
here?
Yeah.
Absolutely. You just have to understand how to do the -1 part.
Could you just plug it into the calculator? Like, are we allowed to use calculators?
Yeah, of course you're allowed to use a calculator. Yeah, it'll work on a calculator. Your issue, I can tell you right now, is going to be units. You will be responsible for the units. So the calculator is not going to help you with units. You need to understand how this all works. Okay. Any other questions about that? Okay, the next part asks, what's the overall order of this reaction?
For that one, wouldn't you just add the values that we got?
Okay.
So wouldn't it just be 1 + 1 - 1?
Exactly right. All we're going to do is add these coefficients. So the overall order is going to be 1 + 1 plus our -1, which is just 1, right? 1 + 1 - 1. So the overall order is 1, or we could say first order. Any questions with that? That's really easy. Don't make that one hard, right? You're just adding the exponents. And then finally, it wants us to determine the rate for experiment 3 at this temperature. Experiment 5 for this temperature. How am I going to do that?
Plug and chug.
Okay, using what equations?
Rate equals the K times the concentration of iodine over hypochlorite over times hypochlorite, and then all of that over the concentration of hydroxide.
Yeah, right. We're just going to use the rate law that we've already determined. Okay.
Can you move your paper up, please?
Oh, I'm sorry.
Thank you.
Trying to keep the numbers on the thing. Okay, now, oops. What about, so I am looking for the rate. So what is the value of K?
.9833.
Yep. And I'm going to actually use the unrounded value since I have it, right? So I'm going to say that K then is simply the 0.9833 per second. And then the concentration for experiment 5, the iodide, is 0.015. And I'll just call it molar, right? You could call it moles per liter. The concentration of the hypochlorite is 0.025 molar. And the concentration of the hydroxide for experiment 5 is 0.005 molar. So I can see that the moles, 2 of the molars cancel, well, 1 of the molars cancel, top and bottom. Plug that into your calculator, and you're going to get 0.1229 molar per second, right? That's what's left, molar per second. We have 2 sig figs, 2, 2, 2. They all have 2 sig figs, so this will be 2 sig figs. So this would be equal to 0.12 molar per second. Or if you use the moles per second, that would be equal to 0.12 moles per liter per second. Either one of these are acceptable. Either one. I don't care which one. Don't give both. Don't give me extra work, because if you give me extra work and it's wrong, I'm going to mark it wrong. Okay, so be careful with that. But I would accept either one of those answers. Okay, any questions about method of initial rates? If you get this on the exam, these are going to be the same types of questions I'm going to ask. What's the rate law? Determine the rate constant, overall and possibly individual orders, and maybe give you some experiment which you need to determine the new rate.